Good evening, everyone. It is so wonderful to see you all here today. Thank you for coming. I'm really excited to host our Enlightening Minds event tonight, and I'll hand over to our pupils who are going to introduce our speakers as well. Just before we start, we are not expecting a fire alarm to go off, so please do follow the instructions of our wardens, who will direct you out if there is an alarm. If you are watching online, we are going to have time for some Q&A at the end. So if you would like to engage with and ask a question, please use the hashtag KCS Enlightening Minds on Twitter, and we will be monitoring that for any questions you might have. Thank you.
Verstraete is one of the world's leading quantum physicists, renowned for bridging quantum information theory and quantum many-body physics. He pioneered the use of tensor networks and entanglement theory to tackle some of the most complex problems in theoretical physics, work that underpins advances in quantum computing and simulation. Frank earned his PhD at KU Leuven, held research positions at the Max Planck Institute in Caltech, and later led the quantum theory group at the University of Vienna. Today, he is the Lee Trapnell Professor of Quantum Physics at the University of Cambridge and a professor at Ghent University. His groundbreaking contributions have earned him major honours, including the Leibniz Prize and Belgium's prestigious Franke Prize.
Céline Broeckaert brings a unique perspective to the quantum conversation. A writer, playwright, and scholar of Romance languages, she has dedicated her career to making complex ideas accessible and engaging. Together with Frank, they co-authored Why Nobody Understands Quantum Physics, and everyone needs to know something about it. A book that blends scientific insight with storytelling to demystify one of the most challenging areas of science. Her work shows that you don't need to be a physicist to appreciate the beauty and impact of quantum theory, just curiosity and imagination.
In this Enlightening Minds lecture, this husband and wife team will demystify this essential branch of science. Together, they will unravel the reasons behind the universe's behavior and why it's so essential we understand them.
And just to mention quickly, we do have a few copies of the book for sale at the end if anyone is interested. Thank you.
So thank you very much for this very nice introduction. Good evening. It is this chapel here is almost as high as the chapel of King's College in Cambridge. It's amazing to be here. And so today we want to talk about the story of quantum physics, one of the big success stories in science of the 20th century.
Yes, and what is so special about this year is that we are actually celebrating 100 years of quantum physics, and then one can ask himself, what is it exactly that we are celebrating? What is it that happened 100 years ago? Well, the year 1925 happens to be one of the most important years in physics. You could compare it as like the Enlightenment for physics. In that year, or in that period, there was still a whole series of questions on which people had no answer. Questions like, for example, how old is the Earth? Why does the sun keep on burning? Where is color coming from? And when we hug a tree, why don't we disappear in it? When you go and sit down on a chair, how comes that you don't think through it? Just to say, why is matter hard? Another question, where is this periodic table of Mendeleev coming from? In that period, nobody actually knew. But thanks to quantum physics, people got an answer. And so, because also in chemistry there were a lot of questions, but in that year many things became very clear and many pieces of the puzzle fell into place. So where did this revolution, the quantum revolution, happen? On two places simultaneously. On the one hand, Heligoland, maybe some of you have heard about it. It's a very small island in the north of Germany, very small as you can see. On the other hand, in the Swiss Alps. The protagonists of this year are Werner Heisenberg, who was in Heligoland, which is not a coincidence, because there he thought I can concentrate very well, I will be alone. He was actually also be running away a little bit of his master, Niels Bohr. There he was alone, and on top of it all, as you can see, there are no trees. And Heisenberg was highly allergical to pollen, so that was perfect for him. And then Schrödinger, he was in the Swiss Alps. And simultaneously, but independently from each other, in that same year, they found a quantum theory which made it possible to explain almost everything. And it's quite surprising because both of them, they start from completely different, or they asked completely different questions, used completely different mathematics, had a totally different approach, but at the end, eventually they came to the same conclusions. And just to give you an idea of the formulas that they found, here they are. Now, if you look very attentively, you can see that they have one thing in common, which is the H with a bear, habar, you call it, which refers to the smallest scale. So this means that actually you cannot zoom in at infinity. This is actually the constant of Planck. It's the smallest scale. You cannot go smaller than this. And as you can see, the number of zeros, it means that it's really very, very small. So it means that you cannot, if you're cutting an apple into pieces, you can cut it in ever smaller pieces, but at a certain moment it just stops. And that is what we mean by quantum, the smallest scale. And from that moment on, we enter in a totally new universe with new laws, and that is exactly what we will talk about tonight.
So I understood that many of the students here in the school will study economics, and when people talk about quantum leaps, so what you have to have in mind that this is an extremely small leap.
Now, let's make a little exercise. What do you think would never have existed had the Schrödinger equation not been discovered? Things that everybody uses in daily life, we are surrounded by it, we make use of it. What do you think? Without quantum physics, it would not have existed. Yes, exactly. Transistors, lasers. Related to that, mobile phones, computers, solar panels, atomic clocks. Without quantum physics would not have existed. So we will start by entering into more detail into the most important applications.
Okay, so indeed, so this is, of course, a transistor is probably the most disruptive technology that has been discovered in the 20th century. And it has only been possible because people had been able to solve this Schrödinger equation. Okay, this Schrödinger equation, this complicated differential equation that was written down in one of the previous slides, gave rise to the fact that people understood how electrons behaved in materials. And using these equations, people could engineer new type of materials, these new type of semiconductors, and with this now create basically the transistors. And transistors are, of course, everywhere now. Okay, so this without a deep understanding of electrons, this would not have been possible. But of course, in a very similar technology, there are also solar panels. Solar panels is actually the same technology as transistors. It's actually much simpler even, but all of this is basically making use essentially of the fundamental properties of this quantum. The fact that if you have light consists out of some elementary units, and these elementary units will excite electrons, and this is how electricity is created. So the quantum aspect is crucial in all these applications. But of course, there's many more applications. Lasers. Okay? The gentleman already talked about the laser. The laser is an extremely interesting example of a technology that took very, very long to become reality, but now is everywhere. So the laser was actually discovered, or the existence of the laser was predicted by Einstein. Einstein was working on the theory of relativity, and at some point he was bored, he got stuck, and he said, oh, let me think about light instead. And then he discovered basically, okay, a laser should be able to exist. Then it took 50 years for people to actually make the laser. Then it took another 20, 30 years for actually really kind of creating this in a completely technological context that can be mass-produced, and now, of course, they are everywhere. So you see the time scales that physicists think about and are relevant are extremely long. And that's why this fundamental science, things like quantum physics, are done always at universities. There's no company that can, of course, invest in a time scale of 50 years or more. But there's more than that. There's, for example, MRI. So MRI is absolutely fascinating. So what happens if you're in an MRI machine is that your body is effectively, you create, with a big magnetic pulse, a superposition of your spins in the up and down direction. You're basically one, for people that have heard about the Schrödinger cat, you're basically creating a huge Schrödinger cat in your own body. And using this superposition principle of these spins in your body, you're able to make these beautiful images that are, of course, extremely useful in medicine. Another thing that we use every day, or most people at least, is the atomic clock. You would think an atomic clock, why do we need this? An atomic clock is an extremely precise clock that takes advantage of one of the most important properties of quantum physics. Namely, quantum physics. In quantum physics, if you have an atom, every 2 atoms are exactly the same. You cannot say this is atom A or B. No, if you have an atom and you look at the electronic levels, they're always exactly the same. That means that if you make a clock based on these energy levels of an atom, they exactly will tick in the same way. And this is what is needed to make these extremely precise clocks that can measure the time difference when I kind of receive a signal from a satellite. If I'm standing here or standing a few meters away, I can measure the time difference because there's a tiny little time difference, and this can be measured by these atomic clocks, and that's exactly what allows me to predict where I'm, so to use GPS.
Yeah, sports watches are also all based on atomic clocks. Next one, atomic energy.
Atomic energy, of course, this is one. So of course, if you have a technology that comes up with something completely new, there's also side effects, okay? The atomic bomb is a side effect. Atomic energy could be the solution for clean energy, but that's still completely open. This really depends on the politicians, how they think about this. But this is, of course, a wonderful technology that would not have been there without the understanding of quantum physics.
Now, to understand how our quantum story really started, we have to go back to the turn of the century. And that is not really a coincidence, because in that time frame, many things were happening. Actually, people were a bit sandwiched between the past, between tradition and between the future, between innovation. Also, many things were happening at the level of art, questioning what is it to be someone, questioning identity, authenticity. People were really looking for meaning, for, as I said, for authenticity. But in art, you also have the new tendencies that were born, like symbolism, like impressionism, like Dadaism, all kind of things. Also Freud was again questioning the identity. But of course, what interests us here most is what was happening in science. And in that time, people really thought that everything had been discovered. There were no more new laws to be discovered, so actually it had no sense to go and study science because everything was there. And everybody thought, okay, there is the physics of Newton, this was the reference, this was the standard, that's it. And they also thought that they still thought that everything could be devised into infinitum, always going always smaller. But then, so yeah, that was also mean, as I said, an apple could be cut it in ever smaller pieces. But in a little bit later, there was Max Planck who said, but what if there is a smallest scale? What if it stops at a certain point?
Yeah, there was indeed some puzzle that people got very, they could not solve it. There was the fact that they wanted to calculate if you have some body, so this is some warm body, and they wanted to predict how many electromagnetic waves are there from a certain frequency. It's a very technical topic, but it's not really important what it is. Anyway, it was a puzzle. There was something that didn't fit the classical laws of physics. It didn't fit the laws of Maxwell. And actually, Maxwell, by the way, was a professor in King's College, and I understood that this college is associated to King's College in London. So this didn't fit this theory, and this was like the first time that people realized maybe there is something wrong with our classical theories. Maybe there's some new things. And Planck tried extremely hard and managed to resolve the paradox by making an extremely daring assumption. He said, let me assume that energy is quantized. Let me assume that energy cannot exist in a continuum, but energy comes in some packets. It's either you have one kind of unit of energy, or 2 units of energy, or 3 units of energy, but nothing in between. Okay, so that there's a smallest unit, and this is exactly where this constant of Planck is coming. This H was this very, very small constant that we talked about before. And he says that energy has to be quantized. And certainly, by making this assumption, all these seemingly, these paradoxes disappeared. Okay? And for him, he said, okay, this is just a mathematical trick. This cannot be the reality. This is something that is too strange, but let's assume this and see what happens. And he did this in the year 1900, and nobody really paid attention because it was so against all the intuition that everybody had, that in principle you should be able to divide everything ad infinitum.
Yeah. So to make this a bit more tangible, in the non-quantum world, when you stand on a ramp, you can take every level, every possible level. But in the quantum world, that's different. You cannot step between the rungs. You can only take or rung 1, or rung 2, or rung 3, but nothing in between. That's the main difference. And as Frank said, Planck, he found it so disturbing. It was so much in contradiction with everything he was standing for, say, the physics of Newton, that he thought, yes, it's just a mathematical trick, but eventually we will end up by finding a much better explanation. So he was really puzzled about this.
Of course, because this H is so small, the distance between these different rungs is very small. So if you look at it from the eye, from the macroscopic point of view, like from our point of view, we would never see these different rungs. It looks like a continuum, indeed. So this is where the tension was.
Yeah,
but then something new happened.
Then came the year 1905 with the famous Albert Einstein. And he was actually the first one who took this mathematical trick of Planck serious. He thought, but what if this is really the property of light? And that was, of course, a really big breakthrough.
So he realized that actually what Planck did was not just a mathematical trick, but told something very deep about light, about the fact that light consisted out of particles. Okay? Before that, people were convinced that light consisted out of waves, and people had done lots of experiments to prove this. You can have interference experiments and so further, and it was very disturbing that suddenly somebody would say, no, light consists out of particles. But nevertheless, for Einstein, this was the only logical explanation of why these formulas of Planck worked so well, and he was actually able to do much more with this. He could explain other phenomena, new phenomena, using this concept.
So, and it is really here where starts this weirdness and of physics, this duality of being and a wave and a particle at the same time. And it's only in 1925, so 20 years later, that Schrödinger and Heisenberg were able to find a mathematical explanation for this. So just to say that in science, things take time. That's very important. And also interesting to say is that Einstein was himself, he was also much more convinced about this discovery than his famous EMC squared, because the theory that we now talked about led at the end to much more further discoveries than EMC squared. It was much more disruptive.
Yeah, indeed. So Einstein actually claimed himself that this quantum physics, because he's really like the grandfather of quantum physics, he said that this was his most original discovery, much more original than actually relativity theory and more impactful. And this is also the theory for which he got the Nobel Prize. He did not get the Nobel Prize for this famous theory of relativity, but actually for this work that he did in 1905.
Yeah, and here you see him together with Max Planck. Then, now in the meantime, the experimental physicists did not remain idle neither. So one day in Manchester, there was Ernest Rutherford, he's from New Zealand, and he was doing something quite interesting. He was bombarding atoms with helium. And then he came to the stunning conclusion that atoms had to be mainly empty space, apart from a very tiny nucleus, which had to contain all the mass of the atom. So that would mean that an atom is for 99.99999% just empty, with all the mass concentrated in a very tiny nucleus, which is already very strange, because one can ask, how then is it possible that matter is hard if it's mainly empty space? So again, a new question. And then Niels Bohr, one of his colleagues, theoreticians, and as you can see, I placed him a little bit lower, but I people sometimes say that theoretical physicists are a little bit lower in the hierarchy of scientists.
No, you don't believe this. This is just to annoy me. That's
It's a little inside joke. But he had the epiphany by understanding that these electrons are not turning randomly around the nucleus, but they are turning around the nucleus in clear orbitals, a bit comparable to planets around the sun, and that these orbitals also are quantized, which means that they all have a very clear energy level, or 1, or 2, or 3, and the electrons cannot impossibly find themselves in between two orbitals.
Indeed. So if you draw these orbitals, they have to match. So if they have a certain wavelength, and if you draw this wavelength, if you go around, it has to match with what you had before. Otherwise, they cannot exist. So this is, of course, was extremely revolutionary because Einstein had only talked about light and Planck too. But now Bohr says, no, it's not just light that is quantized. We also need the quantization of electrons, or actually particles. Particles themselves have some quantization. And this was, of course, again, well, this remained actually some mathematical trick. Okay, so using this mathematical trick, Niels Bohr was able to explain lots of things, but nobody really understood what was going on.
Yeah. So, to resume, in 1900, Planck said energy is quantized. Then came Einstein, who said, oh, but in that case, light has to consist of particles. And then there was Niels Bohr, who said, but in that case, orbitals are also quantized. And the next step was electrons are particles. But then the next revolutionary year was 1924. There was the French prince of de Broglie. Louis de Broglie, he was actually a prince, and he made one of the other very famous discoveries. He said, okay, but if waves consist of particles, then particles should also be a wave. Des particules sont des ondes, he said. What does that mean? Because that's very counterintuitive, but that's what quantum is about. Things are not logic, it's very strange. Now, that means that when you have a particle, you can never exactly say it's there. In quantum physics, you don't have certainties. You have the probability that a particle is here the moment when you do a measurement. But the thing is, a particle is in a superposition. As long as you do not do a measurement, the particle is in a superposition of all places at a different time. So what is between my two fingers is a fragment of a wave. And the particle is everywhere at the same time on this place until you do not do a measurement. When you do a measurement, where the amplitude is the highest, you have the most chance to find your particle. If you do again a measurement 50 seconds later, the particle can be again at a totally different
okay, so
place.
So what de Broglie did is basically resolve this whole tension between particles and waves. So what de Broglie said is that every particle consists out of a wave packet. Okay, so a wave packet, so it has some distance, it's smeared out a little bit, and this wave packet is something that depends on the mass, the temperature, many other things. And so this is why, but of course if this wave packet is very small, it looks like a particle. If this wavelength is very large, it looks like a wave. And using this theory, you can perfectly interpolate between all things that were known. Okay, and it turns out that using this formula that de Broglie discovered, you can calculate what this wavelength is, the extent of which this wave packet is extended in space, and the smaller something is, or the smaller its mass, the larger the de Broglie wavelength. So that means if you talk about very light particles, like electrons, they have very, very large wavelengths. If you talk about heavy particles, they have very short wavelengths. So even I have a certain wavelength, but I'm very heavy, so my wavelength is extremely, extremely small. Much, much smaller than you would ever be able to detect with any microscope. But an electron is extremely light and therefore has a very large wavelength. The nucleus is much larger than the electron, and therefore it has a much smaller wavelength, and that's exactly the size of the nucleus that Rutherford discovered. Okay, so and this is, now of course, now we can see when quantum comes into play. If you have these different particles, these different wave packets, and when these wave packets start overlapping, then you need quantum. Okay? Because if you have waves that overlap, you will have interference effects, and these interference effects will annihilate, will enhance themselves, and that's how you get completely new phenomena. But if the distance between the particles is much larger than the wavelength, then you basically don't need quantum mechanics whatsoever. And classical physics will perfectly well describe your whole system. So using this discovery of de Broglie, he really resolved lots of the paradoxes in quantum physics. Something can be a wave and a particle together, and it's really all relative. It's really relative to the distance between the particles. It tells you whether you have to use quantum or classical.
This will make it a little bit more clear.
Okay, so indeed. So this is, for example, a gas of particles, and they are hot, so therefore they have a very small wavelength. And now we are cooling down this gas. And you see these particles get somehow more extended. They get more and more extended, and these wave packets start overlapping. And at some point, they completely lose their identity, and this is just one big soup of particles. And this is when quantum comes into play. So this is how you kind of see the difference between a classical and a quantum particle. This is actually something that pictures an experiment that people can do in the lab. This is a so-called Bose-Einstein condensate, where you cool this down, and suddenly, at some point, there is a phase transition. And the phase transition is exactly when these particles lose their identity.
So very important, it's not because at a certain point there was the quantum theory that the classical theory of Newton was not valid anymore. Everything just depends on the scale on which you are studying. So both go hand in hand. It's just, or it's quantum, or it's the physics of Newton. Now, if particles are waves, what is the wave equation that describes their motion, Frank?
Yes. And this is exactly what Schrödinger did. So if you say that something is a wave, we must have a mathematical formula to deal with this. And that's exactly what Schrödinger did. And Schrödinger discovered that wave function. Okay, it's a pretty complicated wave function. What is very interesting is that this h bar is there. But what is also very interesting is that this is the first time in the history of physics that a complex number, this I, is the square root of -1. Okay, so probably, I don't know to what extent people have seen imaginary numbers in physics, or in mathematics here, the square root of -1, you learn that this is not allowed. Well, in physics, you cannot do quantum physics without taking square roots of -1. And this is exactly this I. So it's a very interesting equation, and it tells you how this wave, the wave that explains the behavior of this particle, depends or evolves as a function of time. And the person who really understood completely the formalism of physics, or basically kind of nailed down what is it now that we are doing. So why is what Heisenberg and Schrödinger are doing? They did something very different. So Heisenberg did not talk about wave functions whatsoever. He talked about matrices, about observables, about things that you measure. And it looked very, very different. But Paul Dirac, a very famous physicist from Cambridge, realized that actually that this is completely equivalent, that there's many different ways in which you can deal with wave functions. There's many different dual descriptions of the same mathematical formalism. And Paul Dirac was an extremely interesting person, and I think you will read some...
He didn't say much, but when he said something, he could be quite funny. I will just quote him now. He said, "I do not see how a man can work at the frontiers of physics and write poetry at the same time. They are in opposition. In science, you want to say something nobody knew before, in words which everybody can understand. In poetry, you are bound to say something that everybody knows already, in words that nobody can understand." So that illustrates how he was.
So indeed, so what was the first big success of quantum mechanics? Using the Schrödinger equation, suddenly it was possible to completely understand the periodic table of elements. Okay, this was something that people had worked on this. People like Mendeleev had constructed part of this table, and just by doing experiments, by looking at properties of particles. But suddenly, quantum mechanics explained everything. You could immediately kind of understand the periodicity, the different electrons. It all had to do with the possible orbits of these electrons. Okay, so these electrons, you put them there, and you can completely predict this periodic table. That was basically the proof that indeed this was correct. The Schrödinger equation gave you the right results.
Now, maybe you noticed that when you talk about quantum physics, that many people have this tendency to immediately think about crystal balls and telepathy and stuff like this. And that's perfectly fine, and if people are helped by believing in this, that's perfectly fine, but we just want to stress that it has nothing to do with quantum physics. There we are studying a totally different level.
These phenomena happen on a completely different scale, and there's no evidence whatsoever that quantum physics has anything to do with telepathy.
Yeah, just to make it clear.
But indeed, so what is the wave? This is still open, so it is still very disturbing. So I have been working on quantum physics basically since I was a student my whole life, and I cannot claim that I understand quantum physics. I get an intuition about it. I have an understanding. I can predict things. I can use it. I can understand experiments mathematically, but really feeling what does it mean? What is this wave? What does it mean is actually very hard. And one of the keys in understanding or trying to appreciate what this wave function is about is actually to go to the theory of information. Okay, so it turns out that this wave function is not a physical wave. It's not like a wave that you see in the sea. It's more a wave, it's a probability wave. It's something like, has to do with information theory. It has to do with the information that you have about the system. So the wave function is not something physical, it's about the information that we have about the system. And that is, of course, extremely hard, and that's the reason that nobody really understands quantum physics. And especially Einstein was very much against that whole formalism. Although he was the grandfather of quantum physics, he did not adhere to the philosophical implications that probabilities are an inherent part of physics. So before quantum physics, people talked a lot about probability theory and randomness, but randomness was only there because we did not have the complete description of a system. If you would have a complete description of a system, if you would do extremely precise measurement, there would be no randomness. This is why randomness appeared, because we don't know exactly what is going on. Okay, what quantum physics showed is that this is not true, that there is an inherent, even if you know everything about the system, there's an inherent part about probability theory, about randomness that plays a role. And I think from the philosophical point of view, this is very liberating.
And of course, many scientists were very reluctant towards the quantum theory because it was so disruptive. And even Louis de Broglie, our French prince, he knew that there was only one way to prove that a particle can effectively be a wave at the same time. That there was only one experiment that could prove it. He didn't do the experiment himself, but it has been done a couple of years later, which is the famous double slit experiment. It comes down to you bombard little electrons one after the other toward a screen in which we have two slits. And when you do that, you see appearing an interference pattern on the second screen. And this is only possible if this particle effectively goes through both splits simultaneously. But of course, the wavelength has to be larger than the distance between the two slits, because otherwise it's impossible for the particle to enter through both splits at the same time. But they did the experiment, and that was the result. It was the living proof, the very tangible proof that effectively a particle has a wave nature.
And a particle can be at two places at the same time.
Yes.
And this is the mathematics. You see this and you can work with this. It's really understanding what is going on. Nobody does.
Yeah, and somebody who took this a little bit into extreme is Erwin Schrödinger with his famous thought experiment with the cat, which consists of, so there is a hermetically closed box in which you have an atom and a poison. The atom is in a superposition of being decayed and not being decayed. So in one branch of the superposition, when the atom decays, there is a poison that's been released and the cat will immediately die. In the other branch of the superposition, the atom does not decay, no poison is released, and the cat continues to be alive. So it's just to say that something can be both one thing and another thing at the same time. And of course, if you want to know if the cat is still alive or if it's dead, you have to look at it. And this also means so that, just to say that as a scientist, you are part of an experiment. You are not an outsider. You really, the fact that you observe something has a direct impact on the experiment, on reality, which leads us.
Yeah, but maybe you can say something more about this cat. Of course, Schrödinger did this because he did not believe in quantum mechanics. No. Although he wrote down the equation, he was in the camp of Einstein. He thought that this was too weird. The predictions that came out of his formula, he did not believe them. He said he came up with this experiment just to ridiculize, basically to say, no, this cannot be true. This is completely ridiculous. A cat cannot be both dead and alive, although this is actually a consequence of this Schrödinger equation. Okay, but
go ahead.
Okay. So what is another crucial aspect of this whole quantum mechanics is that that you cannot. As an observer, as an experimentalist, you're not standing outside of an experiment and observing it. The very fact that you make an observation, you change the system. Okay? The more precise you want to measure something, the more energy you need to use for the light that you shine on your object, and this energy will actually affect the particle and will disturb the particle. So the more precise you want to measure something, the more you will disturb your system. And that's something that is, of course, again, very disruptive. It's very different than what you have in classical physics or in any scientific theory. We always believed, before quantum physics, that as an observer, you're outside of the experiment. You can just observe what is going on. But the very fact of observation is actually affecting the system, and this is where this very famous uncertainty relation of Heisenberg is coming from.
And this was also, of course, also a very interesting concept at the level of the philosophical. I don't know if somebody of you knows Hannah Arendt, but Hannah Arendt and Schrödinger, they knew each other. They went for coffee regularly. And so she said exactly that the answers that you get depend on the questions that you ask, of course. So again, to say that as a scientist, you are not an outsider, you really make part of the system. So it's a very beautiful quote, what she said. Natural science does not simply describe and explain nature. It is a part of the interplane between nature and ourselves. It describes nature as exposed to our method of questioning. Yeah, that's actually the essence, of course.
Yes. Hannah Arendt was, of course, is a very famous philosopher from the 20th century, and she was basically accusing the Germans of being a little bit hypocrite. It's not the fact that they were there during the war, just the fact that they were there, they allowed basically all these horrible things to happen in the Second World War. That is the context, of course, in which she was writing this.
So, until now, we had a look at one particle, but the most interesting things happen when we have two particles or an infinite number of particles. So 1 + 1 is not 2 in quantum physics.
Indeed. So this is actually very interesting. So if you look at this superposition principle, it tells you that any superposition, some particle can be here and there at the same time. But if you look now at two particles, there are certainly many more possibilities. Particle 1 can be here, particle 2 can also be there, and there's an exponential number of possibilities that suddenly emerge. Okay, so there's this exponential growth. From the moment you have n particles, it turns out that the total number of possibilities of having n particles, the total number of possible wave functions, different situations, grows exponential with the number of particles. Again, exponential growth is something that we all appreciate very much since we understand this since we had COVID, that exponential growth is going extremely quick, but this is everywhere in quantum physics, and this is actually the reason why quantum physics is so hard. Okay, the fact that you're not content to just describe one particle, you want to describe many particles. An actual material has plenty of particles, and the wave functions describing many particles have a complexity that grows exponentially with the number of particles. Again, so the whole point of doing physics is that you have this humongous Hilbert space. So this Hilbert space is the space of all possible wave functions. And it turns out that all the physics goes on in an extremely tiny subspace. Okay, there's this small dot in this humongous Hilbert space where all the real interesting physics is going on. And all the big breakthroughs of physics in the last 100 years is actually about identifying properties of that small spot where actually the interesting things are going on. Okay, and so what you need to do physics, the many-body physics, because that's where the real interest is you need some new principles. You need some new organizing principles. And the person who understood this much better than anybody else is actually Emmy Noether. And Emmy Noether, among physicists, and mathematicians is actually revered as much as Einstein. It's very strange that very few people in the general public have heard about her, but she has been extremely important in physics. So she is actually the person who did not just, due to her work, we understand why the laws of physics are what they are. Okay? And she kind of said that it's all about symmetries. It's about trying to understand the symmetries in the system. Because of the symmetries, the laws of physics, like the Schrödinger equation, is exactly like it is, because it's the only thing that is compatible with the symmetries of your system. Okay, so this is something, of course, very abstract, but of course, extremely important.
Noether's brilliance lies in her realization that the laws of physics governing change and motion also conceal a fundamental constancy. She uncovered the key to understanding why the laws of physics are the way they are. While Newton and Galilei displayed genius by guessing specific laws, Noether looked deeper and discovered an organizing principle behind them all: symmetry. And nearly all major breakthroughs in theoretical physics stem from discovering new ways in which symmetries manifest themselves in nature. The simplest example is Mendeleyev's periodic table, where the periodicity reflects how the rotational symmetry of an atom is represented. A more advanced example of symmetry shaping the laws of nature is the Standard Model, which defines the properties of all elementary particles. This model is entirely built around a symmetry group. In essence, quantum physics is a blend of three vital ingredients: a pinch of symmetry, a pinch of conservation laws, and a pinch of evolving insights. The perfect recipe for a three-layer cake. And once again, we are faced with the almost unreasonable effectiveness of mathematics. One key can unlock an entire series of doors. In this sense, Emmy Noether held the true master key in her hands. We hebben nog 10 minuten. 10 minutes.
Okay, good. Okay, so this was indeed, so Céline was reading parts of the book. But so what is one of these symmetry principles that I would really love you to appreciate after this talk tonight? It's actually something that's called the exclusion principle. So the symmetry principle of the wave function, it tells you that if you have electrons, that the wave functions, two electrons can never be in the same wave function. So there's exactly because electrons are identical, they cannot be in the same wave function. Okay, so this is something that looks contradictory, and it is a bit contradictory, but this is by far, this gives rise to by far the strongest force in nature. This symmetry principle that tells you particles are equal and therefore they cannot be in the same state is the thing that is by far the strongest nature. So if I'm not if I'm standing on this wooden floor and the floor is repelling myself such that I'm standing, this is nothing to do with the electromagnetic force or with the nuclear force or whatever force. It only has to do with symmetry. It has to do with the fact that the electrons in my shoe don't want to be in the same state as the electrons in the wood. And that's what is repelling each other. It's by far the strongest force in nature. It is what explains the stability of matter. Okay, and that's what it's all about. Before quantum physics, people had no understanding whatsoever why matter exists, why matter is hard, how do things repel each other, and it's a symmetry principle. And of course, this symmetry principle is forms the basis for everything in chemistry. This exclusion principle of Pauli is actually what forms the basis for most understanding of materials, chemistry, DNA. They can ask what determines the shape of a crystal. It turns out that this is exactly also this exclusion principle that tells you how the electrons will arrange. They will repel each other because they don't want to be in the same state, and that gives rise to the band structure that at the end then also gives rise to things such as the transistor. Okay, color. Okay, color is some completely other phenomenon that is extremely interesting, that has to do with of course, these symmetry properties of light. It turns out that if you have something like a leaf, a green leaf, and light is falling into this leaf, what happens is that these electrons absorb some energy and want to jump to a higher energy. But it turns out that this is only possible if there's levels that are open there. Okay, these energy levels should not be, there should be energy levels that this electron can jump into. And if it cannot jump into this level, it has to reflect the light. Okay, and that's why actually a leaf is green. So if you kind of look at a green leaf, this is pure quantum mechanics at work. What happens is that this electron is excited in the leaf, but it cannot absorb green light, so it has to reflect the green light, and all the other light, the blue and whatever, is absorbed. Okay, this is a purely quantum phenomenon. Okay, so again, the band structure of silicon, purely quantum physics, purely exclusion principles, symmetries, trying to understand how electrons behave. High energy physics is another manifestation of this fantastic kind of insight that symmetries give rise or let you to an understanding how the laws of physics emerge. So there's this whole notion that people have been able to discover what are the fundamental laws. If you kind of go to the smaller and smaller and smaller scale, you get the smallest scale. How are particles built up for? So how can you actually deal with this? And this is what gives rise to this standard model. And indeed, given somehow the fact that you need humongous energies to see something very, very small, that's why you have to build these humongous accelerators. So this is a picture of CERN where they do these experiments. Okay, so I think from the point of view of actual research of what people are doing, instead of this reductionism, always trying to go to the smaller and smaller, what is actually much more interesting in the last 20 years is the opposite, going to larger and larger scales, going to many, 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 many more particles. So what happens if you put many particles together? Suddenly new laws emerge. And the biggest discovery in theoretical physics of the last 40, 50 years has exactly been something that's called the renormalization group. The renormalization group tells you that at every different scale, completely new laws can emerge that you cannot explain from the fundamental laws. Okay, so this reductionism is basically has been proven wrong. It's not because you understand the elementary particles that you can predict how many particles together will act and emerge, and this gives rise to these emergent phenomena. This is actually Anderson, was also a professor in Cambridge, was basically the godfather of this whole field of emergent phenomena. So I think Céline will read a small section about one of the most beautiful emergent phenomena. This has to do with the quantum Hall effect.
So on the night of 4 to 5 February 1980, at around 2 a.m., the alliteratively named Klaus von Klitzing discovered something that was never meant to be discovered, something that no theorist thought possible. Von Klitzing discovered perfection. And the crux of the essence is this: no matter what material is used to perform the quantum Hall experiment, the result remains exactly the same. This is the perfection of von Klitzing. The caveat, of course, is that your sample must be large enough and, strange but true, contain small amounts of impurities. It's precisely these impurities that allow us to see the quantum Hall effect. So the imperfections are not an obstacle, but a prerequisite for success, however counterintuitive that may seem. This is the power of emergent behavior. More is different. Emergence leads to the most unexpected phenomena. Here we have perfection born out of imperfection, a Greek tragedy rewritten as a triumph. So to end, we will have a closer look at the second quantum revolution.
Yes, indeed. So what is going on nowadays is extremely exciting in physics. So there's actually a second quantum revolution going on. So what is this second quantum revolution? It started around the turn of the century, again, like around the year 2000, where people started to be able to manipulate individual atoms. So people are able in a lab to create some special optical lattices in which they trap atoms, and they can address the individual atoms, see the electrons, study what happens when you do this. So this is something that the founders of quantum mechanics could only have dreamed of. People like Schrödinger and Heisenberg, they would never have thought that this was possible. And you see an actual lab, so this is an actual lab in Cambridge. This is extremely complicated to do this. There's all these lasers and light beams and all these kind of things to be able to do this. But this is exactly what somehow the second quantum revolution is about. What can you do when you start addressing and manipulating individual atoms? Okay, so it turns out that what you can do is entangle these. You can make use of this bigger Hilbert space. As I said before, the difficulty in doing quantum physics is the fact that this Hilbert space, the number of possibilities, explodes exponentially with the number of particles. But of course, this is also a blessing. Okay, you can do it, it's a curse because that makes quantum physics so hard. But if you can create these very interesting superpositions, you can maybe use them to solve interesting problems because you have this exponential space at your distribution, you can actually use this thing. And this notion of entanglement, again, Einstein was at the origin of it. Einstein said, okay, this is ridiculous. This cannot be true. This entanglement turns out to have very strange phenomenological, some experimental consequence. It means that you can use entanglement to instantaneously affect something that happens arbitrarily far. And at first sight, this looked to be in violation with relativity theory, but of course, this is not in violation. But it turns out that Einstein did not understand this. But he was again at the origin. And nowadays, people see that entanglement is the key in unraveling many of the open problems in physics, including, for example, the physics of black holes. Okay, so this is a black hole. so people are believing that entanglement is the thing that people have not been able to understand. So quantum gravity, how to merge quantum physics with relativity theory, that's still one of the big open problems. All the students that start physics, they still dream about unifying all these laws. So people have not been able to do this, but it seems that entanglement is one of the main ingredients that people have to grasp to do this. And entanglement is this resource. Okay? So using entanglement, you can do things much more efficiently than you can do with classical means. So one of the properties is cryptography. You can start making secret bits. You can do something that is called quantum teleportation. Okay, so the person sitting next to my office is Richard Jossa, who discovered this notion of teleportation, how you can actually teleport a particle from some place to a completely different place. This is actually a reality, and people do this in the lab. And using these ideas, people are actually building quantum computers. Okay, so who are the big heroes in building this or understanding quantum computers? There's in the middle, there's Peter Shor. He's the first person who realized that you can actually do interesting things with quantum computers. Above him is David Deutsch, who is the professor in Oxford, who was the first one to realize how to formalize, how to describe quantum computers. And then at the bottom, these are two colleagues with whom I have been working a lot, Peter Zoller and Ignacio Cirac. And these were the people that realized that a quantum computer can actually become reality. This is something that you can do in the lab. It's not just some thought experiment now. There's some effective way of building quantum computers, and this is basically what people do. And so these quantum computers, they basically can take advantage of entanglement to solve problems exponentially faster than a classical computer. Okay, and one of the puzzles that a quantum computer can solve exponentially faster than any classical computer is factoring. I give you a large number. Okay, this is still a very small number, but still, I think there's very, very few people in the audience that know how to factor this number. Okay, like if you factor 6, this is 2 times 3. If I ask you to factor 323, you see this is already very, very hard. And indeed, this is a very hard problem. And the complexity, the security of the internet, whenever we exchange messages on the internet, this is secure because it is so hard to factor large numbers. Okay, this is very hard with classical computers. Quantum computers can actually use this interference effect to do this instantaneously. And that's why a quantum computer would be extremely disruptive. Okay, so what is the bottleneck? So why people, for the moment, there's actually humongous resources from both companies, countries, many governments put there to build such a quantum computer. What could you do with it, and why is it so hard to build this? This turns out to be exactly this same issue that plagued this cat of Schrödinger. Why don't we see a cat that is both alive and dead? Okay, this turns out that the reason that we don't see this is because of decoherence. It's very, very hard to isolate a quantum system from its environment. And whenever a quantum system interacts with its environment, the environment will affect the quantum information, will affect this superposition and break it down, okay, break it completely. And of course, so now people are actually trying to construct this, okay? So these are like papers. So you see nowadays, actually in the last years, all the research, the big research has been taken over, not anymore by the universities, but by all the big companies, IBM, Google, Amazon. These are the companies that are now investing hundreds of millions or billions of dollars in trying to build these quantum computers. And what is the bottleneck that they have to overcome? This is this error correction. So why do they do this? Why is it so interesting to invest in this? Or what is the future of this? It turns out that a quantum computer is actually a universal lab through which we can simulate the many-body Schrödinger equation. Many things that we want to do in chemistry, in drug design, in physics, in material science, is exactly limited to the fact that we don't know how to solve the Schrödinger equation. Okay, this exponential explosion is the curse. It's what makes physics so hard, and it prevents us to make interesting new materials. And the hope is that quantum computers would be able to do this. Like one of the big things that we want to do with quantum computers is to create high temperature or room temperature superconductors. If you would have something that is superconducting at room temperature, this would of course be extremely disruptive. Your cell phone would you would only have to charge it once every week instead of every month or every year instead of every day. Okay, from the point of view of physics, there's no reason that this does not exist. The reason that we are not able to make them is that we don't understand the equations. We cannot write down or to basically solve the Schrödinger equation for the situations in which this happens. Okay, so this whole idea of a quantum computer to be able to solve all the physics and chemistry problems is, of course, the reason that people really want to build a quantum computer.
So to conclude, as you have seen, quantum physics is not just the invention of one person, one scientist in his ivory tower, saying one day, Eureka, I found it's really the interplay, the collaboration between many scientists, and I'm really happy that I could discover that there were also many women among them. I paid a lot of attention to mention them. There is Marie Curie, which everybody knows. Now you all know also Emmy Noether, but there's also Elise Meitner. There are many other women who are really took their place in the history of quantum physics, and I see that a lot of young girls are here present tonight, so I could only stimulate you to go for it because you are as brave as all the other men. So at the end, we come to the final conclusion that quantum mechanics works. No theory of physics has ever had such spectacular success. From ignorance about the structure of matter, quantum mechanics has brought us in less than a century to an understanding so broad, powerful, and precise that virtually all contemporary technology relies on it. And the theory has enabled us to make sense of phenomena far beyond anything technology has yet been able to exploit. And this, despite the fact that nobody understands quantum physics. And just to conclude with a very beautiful haiku that was written by our former minister in Belgium. He wrote it especially for our book, Herman van Rompuy. He says, "The invisible uncovers the visible. Knowing more brings joy." Thank you very much for your attention. Are there questions?
Yeah, thank you so much for the talk. We'll open the floor to a Q&A now. So starting with a question from Holly, I think.
So I found it really interesting how your collaboration looks at both physics, but also arts and philosophy. How do you think that the humanities can contribute to greater public understanding of quantum physics?
Well, I personally think that that physics is just part of a cultural canon. Okay? So actually the whole reason that we started writing this book is that I got interviewed in Belgium by a journalist, and in this interview I said that I did not understand that people would go through great pains reading War and Peace of Tolstoy. I don't know if you read this book, but it's very complicated. You have to take notes. There's all these different persons, and you have to take notes. And people don't have any trouble doing this. They do this with pleasure. But trying to read an even bigger masterpiece, namely kind of how nature works, how quantum mechanics works, this is something that most people would not do. And I said in this interview that I did not understand this. That in some sense, this is just part of our cultural canon. And I think there is no difference between humanities and physics. It's all part of the same kind of things that we want to understand. And if you want to understand how the world works, if you're interested in the world, then you should also know something about physics. So actually, one of the interesting thoughts that we have in mind when we wrote this book was one of the images that we had in our mind was actually very much inspired by a book that is very much in the canon of the humanities. It's called The Perfume of Suskind. So maybe some people have read this, and it's actually a fantastic book. It's a book about some person who kind of has this amazing sense of smell. And he smells many things that nobody else sees, okay, that nobody else smells. And if you read this book, there's a whole new world that opens up. Many, many things that you didn't smell before, suddenly you start smelling.
Or you think you can smell them.
Yes, and no, but suddenly you do smell them. So there's a whole new kind of dimension that occurs. And this is exactly what we wanted to obtain with this book, that if you read this, if you know a little bit of quantum mechanics, there's certainly a whole new dimension in the world that you see that is actually absolutely beautiful, and that you start being able to appreciate, like the color. The fact that if you see a color, that this is a purely quantum effect. That somehow, if you're being repelled by the floor, this is actually the exclusion principle of Pauli that is doing this. All these things, I think, just make everything more interesting and more beautiful.
Thank you very much.
Thank you. So we'll open the floor to everyone. We'll open the floor to questions for everyone now. So if anyone has a question, just put your hand up. We can bring the microphone to you. Yep.
So in your book, you said that the standard model is really based on symmetry, and then you talked about how important really symmetry is. But so are you supporters in supersymmetry? Because like you said that the standard model is like based on symmetry, even though it's got quite big gaps, no? So would you, even though there's been like a standstill in recent supersymmetry like research, are you still like supporting that kind of training thought?
So supersymmetry is certainly not accepted. Like this is a possible theory, but there's no experimental justification whatsoever for supersymmetry for the moment. Okay, so people actually had hoped that they would see signatures of supersymmetry in CERN, but this has not realized. But there's a very big difference between supersymmetry and the standard model. The standard model, there's actually no prediction, nothing that has ever been measured that is in contradiction with the standard model. The standard model really seems to be the thing. Okay, there's nothing that people have seen. Of course, as physicists, we can never prove that a theory is right. Okay, as a physicist, we can only disprove theories. Okay, and nobody has been able to disprove supersymmetry, but certainly people have not seen it in the regimes that people would have thought it was. Also, whether quantum mechanics is the final theory, nobody knows. Nobody knows whether this is the final theory, but any theory that will supersede quantum mechanics will have to include it in some way. Exactly like quantum mechanics also includes the theories of Newton and of Maxwell. All of it is there. It's really like we try to explain, it has to do with scales. If you look at very small particles, and if the particles are far, the wavelengths of the particles are much, much smaller than the distances between the particles, that's when classical physics enters. But once these wave functions start overlapping, you need quantum. So there's all about different scales. And nobody, I think no physicist actually truly believes that quantum mechanics is the final theory. But it's certainly a theory that seems to explain everything that we have here on Earth.
Almost.
Yeah. What's your view on how long it might be before quantum computers may decrypt?
10 years.
Yeah, so this is a very interesting question. So I started working on this in this field of, my main interest is in many-body physics, but I also have been working on quantum computing since the late 90s. And people have always said that the fully working, functional, fault-tolerant quantum computer that can factor large numbers is 10 years in the future. Okay, so we are now like almost 30 years further.
But they said that also 20 years ago,
exactly,
in 10 years.
and it's still 10 years.
Next year they will say again 10 years.
So I don't know whether it will ever be built, but I think it's extremely interesting nevertheless. So what we are seeing these days in theoretical physics, but also in condensed matter, in chemistry, is that this whole field of quantum computation has given us a new language for tackling the central problems in physics. And that's where the real word is. Okay? So this whole field, this whole theory of quantum information has given us a new tools to describe many body wave functions. And that's where all the big problems are in physics, in chemistry, and that is the future. So even if a quantum computer is never built, it has led to a completely new understanding of the central problems in physics. Yeah, it's a very good question, and it goes really at the heart of what we don't understand. And indeed, nobody has a good answer actually to this question. But of course, I think first of all, it's important to see that as a human has nothing to do with the question. It can as well be some photon that basically entangles itself with the box and sees it. It's not that our consciousness has anything to do with the act of observation. Some very kind of abstract some apparatus can also do observations. But nevertheless, what quantum mechanics seems to tell us is that indeed this whole notion of realism has to be retarded. That this is a naive way of thinking about what happens at the microscopic world. That this whole idea of realism, that something is like that and not else, and this is the actual properties of this thing, that this really depends on how you look at it. And this is this whole notion of contextuality. Depending on how you look at it, you will see different properties. And that means that you have to abandon the whole notion of realism. Okay, that's the philosophical consequence of quantum mechanics. But how? We don't know, but it's mathematically consistent, but we don't understand. Okay, that's the whole point. So indeed, it is pretty surprising that after 100 years, we are still struggling with these basic questions. So the main attitude of physicists, my colleagues, including myself, is something that, sorry for my word, but it's called shut up and calculate. Okay, so these questions, if you start asking these questions, this is the end of your career, because you will never solve them.
How does something like quantum tunneling work?
So quantum tunneling is indeed an extremely interesting phenomenon that is exactly responsible for radioactivity. So basically it tells you that if you have a system with electrons or with atoms, like in the nucleus, and there's a very big barrier, some very big energetic barrier through which these particles should not be able to tunnel. Nevertheless, because it's a wave, there will be a small probability that particles will tunnel through. And this is just, again, a consequence of the Schrödinger equation. We understand tunneling because we solve the Schrödinger equation. We see that this is a consequence. And we see that, indeed, things that should be impossible from the classical point of view are possible in quantum. And they have, of course, huge effects. They are responsible for radioactivity, for many, many other phenomena. Actually, the Nobel Prize in Physics this year was exactly about tunneling. It was exactly about you have two superconductors, and there's electrons tunneling from one layer to another layer by some macroscopic thing. It's very, very complicated, but this is exactly what tunneling is about.
My question's more about the education of quantum physics. And you've written a book, so you obviously think it's important that people learn about quantum physics. But as quite a complex idea, when you look at these really long equations and all the complex mathematics behind it, do you think it should be something that is taught more conceptually at an earlier age so people can grasp the thought process behind it before they dive into equations?
Yeah, that's actually a very good point. So this is something that we discuss a lot with colleagues. So what does it mean to understand something? So understanding something is having an intuition about it. Like when I discuss with my colleagues and we come up with some new theory, we say, I feel that it has to be like that. That's the words that we use. So it's all about some intuition. So you have, of course, this huge mathematical luggage that you carry with you, but nevertheless, if you start thinking, the way we think about it is really in terms of images, in terms of analogies, in terms of, because that's the only thing we can do as humans. And indeed, this is the essence, and I think this was one of the main points that we wanted to obtain with this book, with writing this book, indeed, that there's very intuitive principles underlying quantum mechanics for which you don't need any mathematical knowledge, because at the end, the way we think about it, and this is exactly, the book is really written in the way that we physicists, working physicists, think about it, we don't think in terms of formulas. We think in terms of pictures, in terms of analogies.
And also, with the book, we want to stimulate young people, but actually everybody, to ask questions, to question everything, because we are used maybe to take so many things for granted. But it's interesting to think about, so, okay, he has a gray jersey. How comes that it is gray? Why are things hard? Just ask very stupid questions, questions that children would ask. And that is actually something that we have in common. We discovered it in a very early stage. I have a cultural background. Frank has a scientific, academical background, but there is this one thing that we have in common. This is creativity. Creativity in how do you approach things. Being intelligent, what does it mean? It means how do you solve things that you do for the first time? It's being creative in the things that you do and the way that you approach things. Somebody can have the highest degrees, but if he is not creative in the way he is asking questions, he will never be able to do an interesting job. Some other people do not have the highest degrees, but they are very creative and they find the interesting problems to work on, and they will at the end go much further in their life. So it's why do we do mathematics? Because it helps us create in a creative way. I was very bad in mathematics, but now I understand, should I have had better teachers, it would have been much more fun. It can be fun. For me, it's a little bit poetry. It's a language on itself. I don't manage it very well, but I think it's all a question of teaching it in the right way. So it's also a message to teachers. If you enjoy something, then it can be really a beautiful thing.
Do you think it will be possible to incorporate gravity into the standard model in the future?
Yes, sure. This at some point people will be able to do this. Maybe we'll have to abandon quantum physics for this. But there's still so many things that we have not explored, and exactly the one of the main points that we want to make here is that we understand very few things about the many body problem, and quantum gravity is actually something that has to do with many things. And these emergent phenomena, we are only at the start of understanding things. Okay, so this is this paradox. No? All technology that we have nowadays are built on quantum mechanics, but we still understand very few of it. And quantum gravity, I don't think nobody really thinks that this is fundamentally incompatible with quantum mechanics. Somehow these two things have to go together. We just have not found how.
In 10 years.
Okay, thank you so much. I think that was our last question with the timing.
Oh, yeah, last one.
Yes. So indeed, there was a picture of Shannon. Shannon is the first person to understand information. So Shannon was a person who understood how to quantify information, how to look at information and what information is. And that turns out to be very much related to the wave function. The wave function is about information that we have about the system. So it's not a physical wave. A wave function is the information that we have about the system. And that's where information theory comes into play.
Thank you so much. Thank you very much for the talk. It was very educational. Thank you.
Thank you. Ik ga aanbieden. Shut up and calculate.
Okay, and now we have some books for sale at the end. If anyone is interested, that'd be really nice. Thank you.
Okay. Thank you so much for your enthusiasm.